Welcome to our Quantum Deep Dives.
Hello there.
Today, we're jumping into the really foundational work of Nicolas Gisin, a huge name in quantum science.
Absolutely. And we're working from this really insightful essay by Jurgo Schneepat.
Right. And our goal here is to sort of unpack what Gisin did,
Yeah.
his experiments in quantum communication, crypto.
And also the big philosophical questions that his work, well, it really forces us to think about. We want you to see why he's so important for understanding where quantum physics is today.
Okay, so let's maybe rewind a bit. Quantum mechanics. When it first showed up, early 20th century, it was a shock to the system, wasn't it?
Oh, completely. Yeah. Classical physics, Newton's world, everything predictable, local, seems solid.
And then Planck, Einstein, Heisenberg, Schrödinger, Bohr, they started uncovering this.
Yeah.
Well, this other reality.
A reality that seems based on probability, non-locality, this inherent randomness. Very different from the clockwork universe picture.
Yeah, classical physics is like, if you know everything now, you know the whole story, past and future. Deterministic.
Exactly. But quantum mechanics says, well, hold on. Things aren't always in just one state. They can be in multiple states at once. That's superposition.
And they can be linked, entangled, across huge distances in ways that just don't make sense classically.
Right, that's entanglement. And non-locality is this idea that the measurement outcomes seem genuinely random, not just because we don't know enough, it's baked in.
But people push back hard on these ideas. Einstein, famously, with the EPR paradox. He wasn't convinced about this non-locality stuff.
He called it spooky action at a distance. He thought quantum mechanics must be incomplete.
But then John Bell came along.
Bell's inequalities. Crucial. He gave us a mathematical way to actually test if this non-locality was real or just some theoretical quirk.
And the experiments.
They've consistently shown Bell's inequalities are violated, non-locality is real. The universe is spooky, it seems.
So where does Gisin fit into all this? The pioneers set the stage. The debates happened.
Gisin is kind of the bridge figure, you could say. He took these really fundamental, sometimes fiercely debated ideas, especially entanglement and non-locality, and he didn't just talk about them, he built the experiments.
He made them practical.
Exactly. He showed they weren't just philosophical talking points. He demonstrated them working outside the pristine lab environment, connecting that early theory to what we can actually do now.
Right, bringing it to life. And this is where his experimental work becomes so key. He wasn't just confirming theories. He was building things like quantum key distribution, QKD.
Yes, QKD. Gisin was absolutely central to making that practical.
So QKD is basically using quantum effects to make sure communication is secure.
Right, precisely. The core idea is that quantum states are fragile. If someone tries to eavesdrop on the quantum channel used to create the encryption key,
they disturb it.
They inevitably disturb it. And that disturbance can be detected by the legitimate users. So, snooping is physically impossible without leaving a trace. Physics itself guarantees the security.
And the BB84 protocol is like a classic example of how that works.
It is. Using photon polarization states to build up a shared secret key. It's foundational.
But Gisin's team, they pushed this way beyond short distances in labs. People were skeptical, weren't they, about maintaining entanglement over, say, optical fibers?
Hugely skeptical. There was a lot of doubt whether these delicate quantum states, especially entanglement, could survive the noise and loss in real-world fiber optic cables over significant distances.
But Gisin's group did it.
They did. That 1997 experiment, it was a landmark. Transmitting entangled photons over 67 kilometers of standard telecom fiber, under Lake Geneva, actually.
Wow. 67 kilometers.
Yeah, and it wasn't just sending light, it was proving that the entanglement, that non-local quantum connection survived that journey. They performed Bell tests over that distance, violating the inequalities, giving incredibly strong evidence for non-locality operating outside the lab.
So that 67 kilometers wasn't just a distance record.
No, it was proof of principle. It showed that the fundamental weirdness of quantum mechanics could potentially be harnessed using existing infrastructure. That suddenly made things like quantum communication networks seem, well, possible, not just science fiction.
It moved it from, weird, to, maybe useful.
Exactly. It laid the practical groundwork for thinking about secure quantum communication on a larger scale.
And what's so interesting about Gisin is that he doesn't just, build the gear and run the tests. He really digs into the philosophical side, too.
Oh, absolutely. The experimental results directly feed his thinking about the nature of reality.
Like this whole randomness thing.
Yeah.
Classically, randomness is just ignorance, right?
Right.
We don't know all the details, like with a coin flip.
Right. If you knew everything about the flip, the force, the air currents, the coin's imperfections, you could predict heads or tails. It just looks random.
But quantum mechanics suggests something different.
It really does. The outcomes of quantum measurements, especially in tests violating Bell's inequalities, seem to be fundamentally random. Not just unknown, but intrinsically unpredictable. Gisin takes this very seriously. He argues it's a genuine physical feature of our universe.
Okay, so if there's real randomness, how does that connect to something like the block universe? What even is the block universe?
So the block universe idea, often linked with Einstein's relativity, pictures space-time as this fixed four-dimensional block. Past, present, future, they all just exist simultaneously, like frames on a reel of film. Everything's already laid out.
A deterministic picture. Everything is set.
Very deterministic. But Gisin looks at quantum randomness and says, hang on. If outcomes are truly random, then the future can't be entirely fixed like that.
It contradicts the block idea.
Pretty directly. He argues for a more dynamic view of time as something that flows, that becomes. These random quantum events, maybe even our choices, genuinely shape what happens next. The future is open, not predetermined, and sitting there in the block.
That's a radically different feel for reality.
It is, and it leads him to connect quantum physics with free will.
How so?
Well, the question he raises is powerful. If the universe isn't strictly deterministic at its most basic level, if there's genuine unpredictability, does that open up a space for real freedom, for choices that aren't just the inevitable consequence of prior causes?
So instead of being cogs in a deterministic machine,
maybe conscious agents can leverage this fundamental randomness to introduce genuinely new things into the world. It's speculative, of course, but it suggests quantum mechanics might provide a physical basis for authentic choice, which, has massive implications for how we think about responsibility, ethics, everything.
Wow. Okay, that's mind-bending stuff. Let's maybe pull back to the more tangible applications for a second. Where is Gisin's work being used now?
Well, the most direct application is QKD. It's already being used, particularly in finance and government sectors. Anywhere data security is absolutely critical.
And the big selling point is its future-proof nature against quantum computers.
That's a huge one. We know powerful quantum computers, when built, could potentially break much of today's standard encryption. But QKD's security is based on physics, not just mathematical complexity, so it's inherently resistant to those kinds of future attacks.
And looking further out, the quantum internet.
That's the grand vision, yes. Building on Gisin's demonstrations that entanglement can be maintained and distributed, we're talking about networks that don't just send classical bits faster, but transmit quantum states, like entangled pairs across nodes.
Enabling what exactly?
Things like globally secure communication, obviously, linking quantum computers together for distributed quantum computation, maybe ultra-secure ways to handle sensitive medical or defense data, entirely new possibilities based on harnessing entanglement directly.
But getting there, that's not easy, is it?
Oh, definitely not. Huge hurdles. Signal loss over long distances is a major one. You need things called quantum repeaters, which are complex. Standardization is another big challenge, getting everyone to agree on protocols.
And the cost, the politics.
All of that. It's a massive engineering and societal undertaking. But Gisin's work showed the underlying physics wasn't the fundamental barrier some thought it might be.
And his vision isn't just communication, right? It connects to other quantum tech.
Right. Quantum computing itself, obviously, but also things like quantum sensors, using quantum effects to make incredibly precise measurements that could change fields from material science to medicine.
And he really emphasizes this link between the science and the philosophy.
He does. He sees understanding the fundamental nature of reality, tackling those deep questions, as crucial for driving real innovation. He even suggests it could inform how we approach things like artificial intelligence development, ethically and conceptually.
It's clear Nicolas Gisin is a major figure. His standing is, well, it's huge.
Undeniably. You see it in the recognition he's received major awards like the Marcel Benoist Prize, the John Stuart Bell Prize. These aren't handed out lightly. They reflect really fundamental contributions.
And it's not just his own research, is it? He's also trained a lot of people.
Yeah, his influence through mentorship is significant. He's helped shape the next generation of quantum researchers who are pushing these boundaries even further now.
So his career really embodies this blend. physics, engineering, philosophy.
It really does. He shows how tackling these deep, fundamental questions about how the universe works isn't just an academic exercise. It can directly spark transformative technologies.
Like QKD.
Exactly. While at the same time, forcing us to confront our basic assumptions about reality, time, randomness.
His legacy is that bridge, isn't it? Connecting theory to practice, science to philosophy.
I think that's a great way to put it. He demonstrated the power of quantum ideas in the real world while never losing sight of the profound questions they raise.
So, Nicolas Gisin, his work has genuinely reshaped things, both technologically and how we think about the quantum realm. It's a powerful reminder that asking fundamental questions can lead to unexpected practical breakthroughs.
Absolutely, and it leaves us with this really provocative thought to chew on, doesn't it? If the universe does have this fundamental randomness, if the future isn't all written, what does that really mean for us? For time, for choice, for our place in a reality that might just be unfolding moment by moment?
A lot to think about there. We've been exploring the work and impact of Nicolas Gisin, drawing on the essay by Yergo Schneppat.
Thanks for joining us for this deep dive.